Hi everybody, this is Mr. Fasoni, back for more Algebra 2. We're starting up Chapter 4, which is all about polynomial functions. So our first section is Chapter 4.1, the characteristics of polynomial functions. Now the chapter itself is not called that in the book, but we really do talk about the characteristics of polynomial functions more than anything in this chapter. All right, so our goals are going to be to identify and evaluate polynomial functions, and then describe what's called the end behavior of polynomial functions and sketch polynomial functions. The sketching we won't do a lot of, just more of an understanding of the end behavior, which we'll be talking about quite a bit at the end of the section here. So let's get started. The next 3 slides are all about the concept of what a polynomial is. So let's get going on this. So you may recall that a monomial is a number, a variable, or a product or the product of a number and one or more variables. So if you don't recall what a monomial is, I'll just go over that here on the right. I guess I should finish the definition. The product of a number and one or more variables, all with whole number, in other words, positive integers for exponents. So this is a concept that you probably have seen in Algebra 1 and in middle school mathematics classes as well. So monomials can be numbers, so -3, 5, 100, pi, any of these can be considered a monomial. Variables, x, y, z, a, b, c, phi, theta, anything that can be a variable. And then, of course, that last part of the definition, this is probably the more confusing part, the product of a number and one or more variables. So the product is just when you multiply everything together. So a product of numbers and variables and one or more variables, examples could be 3x, 5z, negative 11, a, b, x squared, phi to the third, x squared, y to the 100th, etc. Those can all be considered monomials. So now that we've talked about monomials, we should probably also talk about things that are not monomials. Excuse the bad handwriting. Things that are not monomials are exponents that have powers that are not positive integers. So x to the -1, x to the negative anything really, x to the 1/2 power or x to any fraction, x to the 3.82 power, decimals, definitely not a monomial. And of course, then you've got things like 5 to the x power as well. This is not a monomial. This is actually what's called an exponential. We'll talk about that in Chapter 6 when we talk about logarithms and exponents. So these are examples of things that are not monomials. So going back to finish out the definition, mono means one, while poly means many. And you might recall that from your social studies classes when you learned about world religions. A monotheistic religion would be a religion that worships one deity, where a polytheistic religion would be a religion that worships many deities or acknowledges many deities or whatever, right? This is math though, so we'll stick to numbers and variables. So polynomial is a monomial or a sum of monomials. So polynomials encompass all of the monomials. So 5, -x, x squared y, z, pi times x squared, etc. All of those are polynomials, even though they are also monomials. And then the sum of monomials, that means we can have things like our good friend, the quadratic. 5x squared minus 3x plus 13. That would be considered a polynomial because it's a sum of 3 separate monomials, 5x squared, negative 3x, and positive 13. So that's the basics on polynomials. Let's continue on to the next part. So we define polynomial functions in the form f of x equals, and then we've got this string of crazy stuff going on. We call these a values whenever there's a subscript like n or n minus 1 or 1 or 0. We'll sometimes just say a sub n minus 1, a sub 1, a sub 0. Or we could say a1, a0 if we want. So these values, these a values, are what we call coefficients. And then coefficients are another term that you should be aware of from Algebra 1, or even before that. If I've got some kind of monomial, I've got a variable portion and I've got a number portion. Well, that number that's multiplying the variable is what we call the coefficient. So in other words, the coefficient is just the number that multiplies the variable, or the number out in front of the variable. So the a values are all just coefficients with these values, these subscript values, relating directly to the values on all of the variables, the exponents of these variables. Notice that n and n match, n minus 1 and n minus 1 match. X over here would be actually x to the first, and that matches with the 1 as well. So if I were to write a polynomial, three x to the fourth minus 2x to the third plus 5x squared minus 4x plus 10, I could break this up into all my coefficients and then also all my variables. And because of that, I could say that my A4 value, the number that's in position 4, is 3, or the coefficient that's in position 4 is 3. My A3 value is negative 2. My A2 value is 5. My A1 value is negative 4. And finally, my A0 value is 10. So that's all that means. It's just telling us the position in the polynomial, or in other words, which exponent the coefficient is matched up with. So we're talking about an and all these other values. An is what we call the leading coefficient. The leading coefficient is just the coefficient that is out in the front of the polynomial, and it's attached to what we call the degree, which is the highest exponent value in the polynomial. So on our example over here, my degree would be 4. And we would call this a 4th degree polynomial. And then finally, the last value, this A0, it's just a number, but we call it a constant term. We call it a constant term because if you think about this polynomial function, x is our input, and as we change x, it's going to change all of these x values and raise to various powers in the case of the 4th, 3rd, and 2nd power. But as I change the x value, this 10, this very last value, never changes. It doesn't have an x attached to it. It's just a 10. So my x could be negative 5,000. That 10 would still be 10. My x could be 1,000,000. The 10 would still be a 10. All these other values, all these other terms in the polynomial, they're going to change drastically as x changes. But the 10 will always be constant, always stays the same. So A0 is 10. So that's how we structure a polynomial. And then we have a rule that you probably already know, that a polynomial is in standard form. So remember, all of our functions have these different standard forms. We have standard form for quadratics, standard form for linear functions. Now we have standard form for polynomial functions. And that's just when it is written in descending order of exponents from left to right. In other words, the highest exponents are going to be on the left at the beginning of the polynomial, and you're going to go to smaller and smaller smaller and smaller exponents as you go from left to right. Okay. So last concept, we just have some names for polynomials. Some of these you've seen also, but we're going to review them very quickly. So if I'm at degree 0 for a polynomial, that means I have no variables being raised to powers. And we have what we call just a constant function. So in this situation, for instance, I've got f of x equals -14 as my function. Well, it's a constant function, which means that my f of x value never changes, or my y value never changes. If I were to graph that, it would just be a straight horizontal line at y equals, I shouldn't use y, I'll use f of x, at f of x equals -14. It's constant no matter what my x value is. I'm always at -14. So that's what we call a 0-degree polynomial. Next up, we've got a first-degree polynomial, which are linear functions. We've dealt with linear functions since middle school math and Algebra 1. And if I was to draw a little graph of that, we've got this function over here, 5x minus 7, that's in slope-intercept form. With that basic information, I can graph this very quickly. My -7 is my y-intercept, and my slope is 5x. And my graph would look something like that. Some kind of linear graph that cuts through the x-axis at some point. So it's a linear. Next up, we've got a second-degree polynomial. We call those quadratics. That's what we've been dealing with for the last 2 chapters. And again, if I were to graph that, I could just look at my quadratic function. We have standard form over here. We know what the a, b, and c values do. My c value is -9, so my y-intercept is somewhere down here. My a value is +2, so I know it's going to be a quadratic that's shaped like this. And my b value, I think, was +1 or -1, one of the two, +1. So with that, I could calculate my axis of symmetry, and it would give me a graph that looks something like that. So those are the ones that we've dealt with before, but going forward, we're going into third-degree polynomials and fourth-degree polynomials. The third-degree polynomials are called cubics. You can think about like a 3-dimensional object, a cube, right? Or you can think of x to the third power. We sometimes call it x cubed. So a third-degree polynomial has an x or a variable to the third power. And if we graph it, we'll talk more about the shapes of these as we go through the chapter. If we graph it, the graph of the function looks something like this, kind of like a zigzaggy, curvy thing. And again, we see that that x to the third power is the highest power in this function. And finally, we've got quartics. Quartics are our fourth-degree polynomial. If you have trouble remembering it, just think of the first part of the word, quart. Shows up in the words quarter, which there's 4 quarters in a dollar, 4 quarters in a football game, 4 quarters in a calendar year, or you can just take the word quart. A quart is 1/4 of a gallon. So quart stands for 4. And that means we've got a fourth power in our function, x to the fourth. And the graph of those, we'll talk about those more later as well, but the graph of those look kind of like quadratics, but they kind of some of them have a little bump in the middle area, but on the edges, it's very much like a quadratic. Just in the middle, things get a little bit different, a little bit funky. And again, that was a fourth power or fourth degree polynomial. All right, so let's do a few problems really quick. Our first goal is to identify polynomial functions. So we're going to decide whether each function is a polynomial. That's our first step. And if it is a polynomial function, we're going to write it in standard form and then state its degree, type, and leading coefficient. So if I look at this function, I've got f of x equals negative 2x to the third plus 5x plus 8. Well, to check if it's a polynomial, I just need to look at my variables and see what is happening to them. Make sure that I've got exponents for this polynomial for all my variables, and that those exponents are positive integers. So I just go through very quickly. I've got an x to the third power, that checks out. I've got an x, which is really just an x to the first power, that checks out. And then I've got just a number at the end, or a constant term, that also checks out. So that definitely is a polynomial. So my next step would be to write it in the correct order. Well, if I think about this, if I look at my powers again, third power is already written in the first position. The second position is the first power. And then I've got a constant variable at the end. So this is already in standard form. So there's nothing to do for that second step. So now we got to move on to finding the degree of the polynomial, the type, and the leading coefficient. Well, remember, I can break these up. If I want to find the degree, I'm just looking at the exponent. Again, this is very quick. My degree is 3. It's a third degree polynomial. The type is just the name of the function. If you can't remember, I'm sorry, not the name of the function, but the name of the type of polynomial that it is. It's a third degree polynomial, so it's a cubic. So my type is cubic. So really, once I find my degree, it tells me the type automatically. Once you have those memorized, it's very quick, but you can always look it up on the chart. And finally, my leading coefficient, remember the leading coefficient is the number that's multiplying the variable. So my leading coefficient, I'm just going to call this LC from this point on, is -2. And at that point, I'm done. I've got everything for this first function, f of x. See the second one. Second one is g of x equals negative 0.8 x to the third plus the square root of 2 times x to the fourth minus 12. So again, I need to check to see if this is a polynomial. So I'm going to go through my exponents. I've got a third power, that checks out. Fourth power, that's fine. And I've got a constant. Yep, we have a polynomial. Next up, I got to write this in the correct order. Well, my highest power is the fourth power first, so I'm going to write square root of 2 times x to the fourth. That's my first term. Then the second one will be my third power, so minus 0.8 x to the third. And then finally, my last term is just that -12, the constant term that we have. Now it's in standard form. Last part, I got to look at this first term, which is where my degree and my leading coefficient are. So my degree, in this case, is 4. And the type, well, remember the degree tells us that it's going to be a quartic. And then finally, my leading coefficient is the square root of 2. Because remember, square root of 2 is still a number, not as pretty of a number as an integer would be, an integer, shall I say, but it's still a number. At that point, we've got everything we need. So next up, h of x equals negative x squared plus 7 times x to the negative first plus 4x. Let's check to see if it's a polynomial. Second power, that works. Negative first power. Uh-oh, we've got a problem here. This is not a monomial. And since that's not a monomial, that means the whole thing cannot be a polynomial. At that point, we're done. There's nothing more to do because a polynomial has to have every term be a monomial. And since that middle term is not a monomial, the whole thing can't be a polynomial, which means I can't write it in standard form. I don't have a degree, I don't have a type, and I don't have a leading coefficient. So we're done, and we move on. Last one, k of x equals x squared plus 3 to the x. Well, again, we're going to have a problem. The 2 checks out, but we've got an x for the exponent there. That doesn't work. This is not a monomial. It's not a monomial, so it's not a polynomial. And again, this is actually what we call an exponential. Bad handwriting. Let's fix that. An exponential, and again, we'll be dealing with those in chapter 6. So that's the first type of problem we're going to be dealing with, is just determining whether the function is a polynomial function, and if it is, just writing down all the different characteristics of it. Next up, we have evaluating polynomial functions. This is something that you absolutely should know how to do. Evaluating a function is literally just plugging in an x value. So I've got my function f of x, but this function is defined as negative 2x to the fourth plus 6x to the third minus 3x plus 11. But I'm going to evaluate it when x is equal to 4. So everywhere there's an x on the function, I'm just going to replace it with a 4. Oops. Getting ahead of myself. Or rather behind myself, I think. So I put in all this stuff, got all my numbers in there. Once I've got plugged in all the values for x, in this case my value is 4, I'm just using the order of operations. So I'll do my exponents first. It's going to be negative 2 times 256 plus 6 times 64 minus 3 times 4 plus 11. And then we can continue along this by multiplying. We get negative 512 plus 384 minus 12 plus 11. And then finally I can add all this together, or add and subtract, I guess. I'll deal with these first because they're easy. Negative 12 plus 11 gives me negative 1. 384 minus 1 gives me 383. So if I've got negative 512 plus 383, I can do a quick subtraction problem, or I can just plug it into a calculator. Whenever you've got a positive and negative, just do a subtraction problem. Put the larger of the two numbers on top, subtract them. I get 129. And now all I have to do is just look back at my higher of my two numbers, or I'm sorry, not my higher of my two numbers, my larger of my two numbers. My larger of my two numbers is 512, and the sign of the larger of the two numbers is going to follow whatever the answer is. So my answer is negative 129. So f of 4 is equal to negative 129. So when that function is at x equals 4, my output value is negative 129. And that's evaluation. You guys should know that already, but that's a quick review. All right, now time for our second and final concept, the end behavior of polynomials. So this is a little bit weird. We've got this chart. I want to talk about this chart a little bit more in depth, but this is a good reference. But the end behavior of a function, its graph rather, is the behavior of the graph as x approaches either positive or negative infinity. So in other words, x is going either way to the right for positive infinity or way to the left for negative infinity. And all of that can be determined by the two values that are in the very first term of our polynomial, the degree and the leading coefficient. And when we talk about end behavior, we're talking about what the f of x value is doing. So x is going either way out to the left or way out to the right, but then the f of x, the output value, is either going to be going up or down. That's the behavior that's going to be happening. We've got some diagrams here, but I want to talk about this a little bit more in depth. So remember, we had the degree and the leading coefficient. Those are the two things that they say are the determining factors for this. Well, let's break this up into a little chart here. So if we think about degree, the degree of a polynomial can be broken up into either an odd degree or an even degree. And the leading coefficients, I can view those as either positive or negative. What we get is kind of a little diagram like we've seen when we complete the square. We get four situations. If my degree is odd, for example, if I have something like x to the 5th power, and my leading coefficient is positive, so maybe it's a 2, my function is going to look like, I should move this. Let's see here. If I've got something like 2x to the 5th, my function is going to look, in general terms, something like that. And then if I have an odd degree with a negative coefficient, again, I'll put these in there. I think I had, what, 2x to the 5th? Let's say I've got negative 2x to the 5th. Well, my function is going to be effectively the mirror image, in general terms, of the function with the positive coefficient. I'm doing a bad job at positioning. Let me see if I can fix that. Next up, we have the even degree and positive coefficient. So for example, maybe I've got uh, 3x to the 6th power. My function, in general terms, is going to look something like this. And then finally, we've got even degree and negative coefficients. And in general terms, it's going to look something like this. Maybe this is negative 3x to the 6th. So what does this mean? What are we talking about with end behavior? Well, end behavior, all it's saying is, let's use pink. As my x value, as I go in a direction, let's fix that real quick. I'm doing all types of weird stuff today. Let's see if I can, okay. As my x value is going, for instance, towards negative infinity, well, what's the y value doing? Well, in this graph here, when it's odd degree and positive for the leading coefficient, as x goes towards negative infinity, my f of x value goes towards negative infinity. As x goes towards positive infinity, to the right, my f of x values go up towards positive infinity. With an odd degree and a negative leading coefficient, as my x values go towards negative infinity, my f of x values go towards positive infinity. And finally, no way. Okay, I think I may have lost my recording for a second there. I apologize if there's a mess up and me getting frustrated and saying no way. I apologize for that. I think my internet lost connectivity for a second there. So let's go back to this. If I'm an odd degree with a negative leading coefficient, as x goes towards negative infinity, my f of x goes towards positive infinity. Similarly, if my x goes towards positive infinity, my f of x goes towards negative infinity. So there's a little bit of a change there. With an odd degree, as we go to the left or to the right, one of the two directions is going to take us towards positive infinity, the other one's going to take us towards negative infinity. With even degree, we have a slightly different situation happening. If I go to the left or to the right, as x goes towards negative or positive infinity, with even degree and positive leading coefficient, my f of x values both go towards positive infinity. And then finally, with an even degree and a negative leading coefficient, as my x value goes towards negative infinity, my f of x goes towards negative infinity, or as x goes towards positive infinity, my f of x goes towards negative infinity as well. So basically what's happening when we talk about end behavior, we're asking in what general direction is the f of x going? Is it going positive? Is it going up? Or is it going negative? Is it going down? As the x value goes out towards negative infinity way out on the left or positive infinity way out on the right. So we have this nice little chart that we can use. This is also in your book, but you can refer to this video as well. And it basically tells all the same stuff, as well it has a little bit of writing, which I'll explain in just a second. So let's do a problem to see what I'm talking about. Excuse me. So goal 2, describing end behavior. So we're describing the end behavior of the graph f of x equals negative 0.5 x to the fourth plus 2.5 x squared plus x minus 1. Well, the nice thing about this is I'm trying to describe my end behavior. If you remember from the definition, it's all determined by the degree and the leading coefficient. So I can just look at this very first term, find my degree. My degree is 4, which is an even number. And then my leading coefficient, my LC, is negative 0.5, which is negative. So I could just kind of refer to the chart until I get it kind of down pat. If my degree is even and my leading coefficient is negative, I'm going to have this kind of letter M shaped thing. So my function should look something like this. And what that means then is if I'm thinking about x, how it relates to f of x, as x goes to the left, in other words, as x approaches negative infinity, as it's going way, way, way to the left, the f of x values are approaching the vertical negative infinity. So it's going down forever. And then if I want to talk about going to the right, as I go to the right, as x approaches positive infinity, I should change colors here. The yellow does not look good on this. Let's go to purple. as x goes to positive infinity, my f of x, my vertical coordinates, are going to go towards negative infinity. So as I go to the right with my x's, my y values or my f of x values are going to go down. That's all we're saying. That's all we're predicting. We don't necessarily know what's going on in this middle area. The little bumps are just kind of a generalized graphic, and they can be wildly different depending on the equation, which we'll go ahead and graph using Desmos really quickly right now. So let me pull this up. Let's see here. F of x equals, was it negative 0.5 x to the fourth plus 2.5 x squared. There's that weird double hump that we had, plus x. Now it looks a little bit weirder, and then minus 1. So as you can see, we've got this kind of distinct look. The function, as we come from the left and move to the right, we kind of hit a hump, and then we go down, come back up. We reach this kind of peak here, and then it goes downhill. So again, what I was saying is we don't really care about what's happening in this area, so to speak. What we care about is what happens as our, I'm going to try to zoom this vertically only, as you can see, I'm not really zooming it horizontally, but as my x values get larger and larger to the left, they go more and more negative, my y values go down, down, down. As I go to the right, as I move away from the origin to the right towards positive infinity, my f of x values go down, 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 down. And I can zoom this out as much as I want infinitely, and you can see that it gets wider and wider. It takes a long time. These x value or the y values get very negative very quickly. You know, by the time I'm at just 25, my my y values have already gotten into the negative hundreds of thousands. So that the x values grow much more slowly in comparison to the y values. But we have predicted that end behavior. And what's nice about that is I can very quickly kind of estimate what's going to happen, even if it's a crazy function. You know, 172 times x to the, I don't know, 37th power, plus a bunch of other stuff, maybe 36 more terms, all the way down to, or 37 more terms, all the way down to some kind of constant at the end. All those other terms don't matter because I've got a positive and an odd degree. I know that the graph in general terms will look something like this. The stuff in the middle will be a crazy mess, but the stuff on the ends, the end behaviors, I can absolutely predict. And again, I could do that in Desmos really quick. I'm not going to write out a full polynomial, but if I have 172 times x to the 37th power, it'll be crazy steep, and it'll grow super, super fast once I get larger than 1. In fact, I can't even probably show that very easily. But once x is larger than 1, I don't even know why I'm doing this. At just 1.013, I'm already at 277 for my y coordinates. So things get very large very, very quickly. And of course, I have that in behavior. If I'm over here on the left, it's going down forever. If it's over here on the right, I'm going up forever. All right, so that's it for chapter 4.1. I'm going to go ahead and post this on YouTube. The homework is due this Friday before Thanksgiving break. I hope you guys are all doing well, and I'll see you soon.